So picture this. You have been printing for, well, a solid year now. Your PLA prints look absolutely flawless.
Right, the first layers are going down like a mirror.
Exactly. You have dialed in your retractions, and you even mastered those annoying stringing issues with PTG.
You are feeling pretty confident at that point.
You really are. But then you print a functional PTG part. Maybe it is like a custom mounting bracket for your dashboard. And you leave it in a hot car in the middle of July.
Oh, that never ends well.
It does not.
Yeah.
Or maybe, you print a replacement gear for a household appliance, you put it under a heavy load, and it instantly melts or warps or just snaps in half.
Yeah, that is the exact moment you realize the training wheels have to come off.
It really is. Today, we are doing a deep dive into some source material provided by Printara 3D. The goal here is to build a practical decision framework so you can graduate to the heavyweights of the FDM world.
And we are specifically comparing nylon, which is also known as polyamide or PA, against polycarbonate or PC.
Right, because it is a completely necessary transition if you want to move from, making desk toys to fabricating actual end-use hardware.
We all know the frustration of a failed functional part. I mean, to understand why you would even subject yourself to the notoriously demanding printing process of these materials, we have to look at the raw numbers first.
Yeah, because nobody is loading up polycarbonate just to print a decorative vase. It is all about the strength and heat resistance.
Exactly. Those are the numbers that draw people in.
So looking at the Printara 3D data, nylon brings some serious tensile strength. Specifically, PA6, which is a really widely used variant, hits around 70 megapascals.
Which a lot. And PA12, another popular option, sits slightly lower. It is around 45 to 55 megapascals.
For a desktop printer, those are heavy-duty numbers.
They definitely are. But polycarbonate really pushes those boundaries even further.
Oh, yeah.
Yeah, the data shows PC delivering 55 to 75 megapascals of tensile strength. But the metric you really want to pay attention to here is its notched impact toughness.
Right. I see that term tossed around on spec sheets a lot.
The source is rated between 600 and 850 joules per meter. That is literally an order of magnitude above standard FDM plastics.
Wait, so notched impact toughness, does that just mean it survives getting hit with a hammer?
Well, it is much more specific than that. Right. And it is critically important for 3D printing. A notched impact test measures how well a material resists catastrophic failure when there is already a small flaw in it, like a notch cut into the surface.
Oh, I get it. Because if you think about the nature of a 3D printed part, it is built layer by layer.
Precisely. Every single layer line on the surface of your print acts as a microscopic V-notch.
Wow, okay. So if a material has poor notched impact toughness, a physical blow will just cause a crack to propagate right along those layer lines.
Exactly. It just shears the part in half. Polycarbonate's high rating means it forcefully resists that crack propagation, even with all the inherent flaws of FDM layer lines.
That makes a ton of sense. Instead of a brittle snap, I imagine it acting more like the plastic bumper on a car.
That is a great way to think about it.
Like when you back a car into a pole at low speed, the bumper doesn't shatter into glass-like shards. It absorbs the kinetic energy, it deforms, takes the hit, and mostly holds its structure.
Yes, and the reason it behaves like a bumper comes down to its molecular structure. Under sudden force, the polymer chains in polycarbonate have the ability to stretch and slide past each other slightly.
Oh, so they absorb and distribute the trauma across the part instead of just rigidly snapping.
Right. It gives you an incredible combination of stiffness and ductility under stress.
I do want to challenge that stiffness aspect, though.
Okay, go for it.
Because if stiffness is what we want, I see this very common trend on printing forums where makers just add chopped carbon fiber to absolutely everything.
Oh, the carbon fiber craze, yes.
Right. So if I take nylon and buy a spool of PACF, carbon fiber infused nylon, doesn't that just make it universally stronger than pure polycarbonate? I mean, in my head, carbon fiber always beats unfilled plastic.
That is probably the most pervasive myth in functional printing right now.
Wait, really?
Yeah, the reality is that adding carbon fiber fundamentally changes how the plastic fails. The short answer is no. PACF is not universally stronger.
But it does make it stiffer, right?
Carbon fiber does massively increase the nylon stiffness, its dimensional stability, and its heat deflection. It will hold its shape under a heavy static load beautifully.
Okay, so where is the downside?
Well, you are introducing incredibly rigid microscopic carbon rods into a flexible nylon matrix.
So they sort of fight against each other when the part gets hit?
Exactly. When a sudden physical shock hits the part, the flexible nylon wants to yield and bend. But those rigid carbon fibers just refuse to move.
Because they don't flex at all.
Right. So the points where the fibers meet the plastic become microscopic stress concentrators. They actually initiate microtears inside the material.
Oh, wow. So while PACF is incredibly stiff, it loses to pure polycarbonate in raw impact toughness.
Yes. If you hit a PACF bracket with a hammer, it is much more likely to shatter. Those fibers act as internal failure points under shock. Polycarbonate, without the fibers, will just absorb the blow.
Okay, so stiffness definitely does not equal toughness. PACF is for static loads, and PC is for taking a beating.
That is a very good rule of thumb.
But, physical impacts are not the only stress functional parts face in the real world. What happens when the environment itself is the stressor, like my ruined dashboard mount baking in the sun?
Heat resistance is where these engineering filaments really leave materials like PLA and PETG completely in the dust. The metric we look at here is the glass transition temperature.
And that isn't the melting point where the plastic turns to liquid?
No, not at all.
Yeah.
The glass transition temperature is the specific thermal threshold where the solid plastic starts to become pliable. It loses its structural rigidity and just deforms under its own weight.
It reminds me of heating up a wax candle. The wax doesn't just instantly turn into a puddle of liquid.
Right, first it gets soft.
Yeah, you can bend it with your fingers and it completely loses all its structural integrity.
That captures the concept perfectly. With pure polycarbonate, that glass transition temperature sits around 145 degrees Celsius.
That is extraordinarily high for a desktop printer.
It is. Now, pure polycarbonate is notoriously difficult to print because of its tendency to warp. So material scientists create modified blends for easier printing.
Like the Prusament PC Blend mentioned in the sources.
Exactly. And even a specialized blend like that is rated for structural use up to 113 degrees Celsius, according to their datasheet.
Which is still well above the boiling point of water. Your car interior in July wouldn't even come close to softening it.
Not even close.
Those numbers are staggering. I mean, you are looking at spec sheet performance that legitimately rivals injection molded parts.
But I know you know there is a catch.
There is always a catch. To actually get that 70 megapascals of strength or that 113 degrees of heat resistance on your desk, you have to overcome a massive shared weakness between these two plastics.
Yes, the sponge problem. Moisture management. The Printora 3D sources stress this repeatedly. Both nylon and polycarbonate are highly hygroscopic.
Hygroscopic meaning they actively pull water directly out of the ambient air in your room.
Yes, they suck it right up.
I think a lot of people assume that just means you might get some ugly stringing or, a few pops and hisses at the nozzle like you do with a wet PTG.
It is far more severe than a few cosmetic pops.
Yeah.
We need to talk about hydrolysis.
Hydrolysis, that sounds serious.
It is. When you take a filament that has absorbed atmospheric moisture and force it into a hot end, sitting at nearly 300 degrees Celsius, that trapped water instantly flashes into steam.
And I'm guessing that steam creates microscopic voids in your layer lines.
It certainly does that.
Yeah.
But the combination of intense heat and water actually triggers a chemical reaction. That is hydrolysis.
Wait, so the water is actively changing the chemistry of the plastic inside the nozzle?
Precisely. Hydrolysis chemically severs the long polymer chains of the plastic. It breaks them down into much shorter chains.
And the entire mechanical strength of these materials relies on those long, entangled chains, right?
Exactly. When you break them, you permanently degrade the plastic. If you print wet nylon or PC, it really does not matter how well the part looks on the outside.
Because the chemical structure has been compromised?
Yes. The mechanical properties we just discussed will be gone. The part will be dangerously brittle.
And there is a real difference in just how thirsty these materials are, especially within the nylon family.
Very much so. PA6 is essentially a sponge. At full saturation, PA6 can absorb up to 9% of its own weight in water.
Almost a tenth of your heavy spool could just be trapped atmospheric moisture. That is crazy.
It is a lot of water. PA12 is much more manageable, absorbing only about 1.5% moisture by weight, but, it is still highly hygroscopic.
Okay, I am going to put on my stubborn maker hat for a second.
I am ready.
I see this advice handed out on forums all the time. People say, look, I just bought a brand new premium spool of nylon. I took it straight out of a vacuum-sealed factory bag, and it even had the little silica gel desiccant packet inside.
Oh, I know where this is going.
Physics says I can just load that pristine spool straight onto the printer and hit start, right?
It is vital we put that myth to rest today. You absolutely cannot trust a factory seal.
But it is sealed from the factory.
Yes, but the manufacturing process of filament involves extruding the hot plastic through long water cooling baths before it gets spooled up. Engineering polymers can and do absorb moisture during the manufacturing process, long before they are ever placed in that vacuum bag.
Oh, I never thought about the water cooling baths. And I suppose that little desiccant packet isn't doing much.
That packet is only designed to keep the ambient humidity in the bag stable during shipping. It simply does not have the pulling power to extract embedded moisture out of the solid plastic core.
So even the lower absorbing PA12, straight out of the shrink wrap, needs to be treated as wet filament.
Treat every single engineering filament as wet until you personally dry it. Moisture management is simply non-negotiable.
Okay, so let's say I respect the chemistry. My spool is bone dry. I still cannot just feed these materials into the stock $200 open frame bed slinger I bought last year, right?
Not at all. The hardware demands are steep. Upgrading to these materials requires serious hardware intervention, and that starts with your HO10 temperatures.
We mentioned Prusament PC Blend earlier.
Right. To print that properly, you need a sustained nozzle temperature of around 275 degrees Celsius.
Which pushes standard 3D printer hardware way past its safety limits.
Way past.
Because a lot of entry-level machines use a standard Bowden tube setup, where the white PTFE tube goes all the way down inside the heating block to touch the nozzle.
And if you push that PTFE tube to 275 degrees, you are stepping into a serious health hazard.
Yeah, that is terrifying.
It is a massive safety risk. PTFE begins to rapidly degrade at temperatures above 250 degrees Celsius. When it breaks down, it off-gases highly toxic, neurotoxic fumes into your room.
Breathing that in is incredibly dangerous. Not to mention it will completely ruin the internal workings of your HO10.
Exactly. You absolutely need to upgrade to an all-metal HO10 where the heat break separates the PTFE tube from the melting zone. That is the only way to safely print polycarbonate or nylon.
And the upgrades do not stop at the heat break, do they? If you were printing those carbon fiber nylons we talked about, the PACF, you need to look at the nozzle itself.
The abrasive nature of chopped carbon fiber is shocking if you've never seen it in action.
It really is. Those rigid little fibers act exactly like microscopic sandpaper flowing under high pressure.
Yes. If you try to print a spool of PACF through a standard brass nozzle, the carbon fibers will literally carve out the inside of the nozzle orifice.
Like a 0.4 millimeter opening will be sanded out to a 0.6 or 0.8 millimeter oval in just tens of hours.
You will lose all flow control and dimensional accuracy. You must swap to a hardened steel, ruby, or tungsten carbide nozzle.
Okay, so we have a high-temp all-metal hood end. We have a hardened nozzle. What about the build plate? Polycarbonate is notorious for warping, so logic says we need it to stick to the bed with an iron grip.
That is the logical assumption, yeah.
Can I just crank my bed heat and squish the first layer down onto a flawlessly clean, bare PEI spring steel sheet?
If you do that, you will likely destroy your build plate.
Wait, really?
Yes. Polycarbonate adheres so strongly to bare PEI that it chemically and thermally fuses to it. Both are high-temperature amorphous polymers.
Oh, so when heated, their polymer chains actually intermingle at the surface.
Exactly. When the print finishes and you flex the steel sheet to pop the part off, the bond between the PC and the PEI is often stronger than the PEI's bond to the steel itself.
You will literally rip chunks of the PEI coating right off your expensive build plate. That sounds like a nightmare.
It is, so it sticks too well.
What is the workaround then?
You have to use a release agent. Ironically, you use adhesive to make it stick less.
Oh, so like a generous layer of simple glue stick or a specialized product like Magic Glue PC?
Right. It acts as a sacrificial interface layer. It holds the hot part down during the print, but creates a physical barrier that prevents that chemical fusion, allowing you to actually remove the part once it cools.
I'm going to be honest, managing the bed adhesion sounds doable, but buying or building an enclosure sounds like a huge hassle.
A lot of people feel that way.
So if I have an open frame printer and I just crank my bed temp to the absolute maximum, slather on a thick layer of glue stick, and run the first layer at a crawl so it really bakes in, physics says the print shouldn't go anywhere, right? Can I get away with printing PC out in the open like that?
I will completely shut that approach down.
Really?
Yes. The issue with printing high-temperature materials on an open-frame machine isn't just about the first layer gripping the bed. The real enemy is thermal contraction.
How so?
Well, imagine your print is halfway done. The bottom layers are sitting directly on a heated bed, staying nice and warm, maybe at 110 degrees Celsius. They remain expanded.
Okay, making sense so far.
But the upper layers, maybe a few inches off the bed, are suddenly exposed to the ambient room air, which is only, say, 22 degrees Celsius. Those upper layers cool down incredibly fast.
And as plastic cools, it shrinks and contracts.
Exactly. So the top of the part is actively shrinking while the bottom is staying wide.
That temperature gradient must create an immense bending force pulling upwards from the top layers.
Immense. Even if your first layer is glued down perfectly, the internal mechanical stress becomes so great that the part will violently warp, pulling the corners right up.
Or if your bed adhesion actually holds, I bet the stress would literally tear the print apart, just splitting the walls horizontally along the layer lines mid-print.
That happens all the time. For these materials, especially the advanced industrial variants like Polymaker's PCFR, PC-ABS, and PC-PBT, the printer of 3D sources explicitly state you require an actively heated build chamber.
So an enclosure is mandatory to keep the ambient air warm and let the entire part cool slowly and evenly.
Mandatory. No exceptions for PC.
All right, so we understand the physics. We know the incredible performance specs, the brutal reality of hydrolysis, and the intense hardware requirements. Let's boil this all down.
Let's do it.
If you are prepping your machine for a weekend project, how do you actually make the call between nylon and polycarbonate? Let's build the decision guide.
It requires an honest assessment of what your part is going to do and what hardware your printer actually has equipped. Let's break it into option X and option Y.
Okay, let's start with option X. When is nylon, specifically PA12 or PACF, the right choice?
You choose PA12 or PACF when the part you are designing involves sliding friction, repeated flexing, or regular contact with oils and greases.
That makes sense. Nylon has a naturally low coefficient of friction and incredible wear resistance.
Exactly. Think of functional meshing gears, sliding bushings for a CNC machine, or custom tool jigs that get snapped in and out of place hundreds of times. Nylon excels there, provided the operating environment stays under 100 degrees Celsius.
And for the hardware side of option X?
PA12 and its carbon fiber blends are the right path if your printer lacks an actively heated chamber. While an enclosure always helps, nylon is generally much more forgiving when it comes to thermal contraction and warping compared to pure polycarbonate.
Okay, so that makes nylon the friction and wear champion. When do we pivot to option Y? When does polycarbonate become the necessary choice?
You stick with polycarbonate when your part is going to take severe physical impacts, or when it has to endure sustained, punishing temperatures above 110 degrees Celsius.
So this is your go-to material for high-stress applications, like custom mounting brackets that sit right near your hot printer bed.
Yes, or underhood automotive clips that have to survive radiating engine heat and constant road vibration without softening.
But the major caveat is hardware.
Huge caveat. You only choose polycarbonate provided you have a fully enclosed printer that can handle the intense thermal management required to prevent layer splitting.
That is a perfect, clean rule of thumb. Nylon is for continuous friction and repeated wear. Polycarbonate is for brute force impacts and high ambient heat.
That distinction alone will save you a lot of failed prints.
It really will. Now, to make sure you actually get to experience those high-performance traits, and you don't just end up with a pile of very expensive, very strong spaghetti on your build plate, we have one critical, actionable takeaway for you to apply this week.
It is the single most important operational habit you can develop when stepping into the engineering tier of filaments.
Before printing nylon or polycarbonate this week, you must dry the spool at 70 degrees Celsius for 6 to 8 hours in a dedicated filament dryer. Skip this step, and the spec sheet strength we just spent 20 minutes talking about simply will not exist in your final part.
It is worth repeating because makers ignore it constantly. You are paying a premium price for these materials specifically for their mechanical resilience.
Right, and if you do not dry them, hydrolysis will destroy the polymer chains, and you are literally throwing that premium money away.
Just imagine the heartbreak.
Oh, I know. You drop 60 euros on a premium spool of PACF. You spend 3 evenings meticulously designing a structural arm for a custom racing drone.
You slice it, you print it out, and visibly it looks great.
Yeah, it looks perfect. You bolt the motors on, take it out to the field, punch the throttle, and the moment the drone takes a hard banking turn, the arm snaps clean off in mid-flight, right along the layer lines.
And it snaps not because the design was bad or the material was weak. It is simply because you skipped the 70-degree drying cycle and the embedded moisture severed the chemical bonds between the layers inside the hot end.
The moisture robs you of the impact resistance you paid for. Invest in a proper filament dryer or, use a repurposed food dehydrator that you know has precise temperature controls.
Just dry your filament. It is the cost of entry for this tier of printing.
It really is. When you finally dial in that drying routine and your hardware upgrades, it completely shifts your perspective on what a desktop 3D printer is capable of.
You move from printing fragile prototypes to fabricating genuine functional replacement parts that often outlast the factory originals.
It really does feel like discovering a new superpower in your workshop. And the fascinating thing is, once you get the printing process perfect, the journey actually doesn't end there.
It definitely doesn't.
There is an entirely different post-processing technique you can explore that pushes these plastics even further. We spent all this time talking about the strength of the parts right off the glass, but consider exploring the process of annealing next.
Annealing is a brilliant next step. It is a concept borrowed directly from metallurgy and glassworking.
So what does that actually look like for a 3D printed part?
Well, it involves taking your finished, successfully printed polycarbonate or nylon part and baking it in an oven at roughly 100 to 120 degrees Celsius for a few hours, and then allowing it to cool down incredibly slowly.
Wait, so you are basically putting the finished plastic back into the heat. Why? What does that do to the internal structure?
During the FDM printing process, the rapid heating in the nozzle, followed by the relatively rapid cooling on the bed, creates intense internal stresses inside the geometry of the part.
So the polymer chains are essentially frozen in stretched, unnatural positions.
Exactly. By baking the part at a specific temperature just below its melting point, you provide those polymer chains with the thermal energy they need to relax, reorganize, and settle into a much stronger, more dense crystalline structure.
Oh, wow. So this thermal soaking releases the built-up internal stress.
Yes, and it can significantly increase the temperature resistance and overall tensile strength of the part well beyond its original printed state.
You are literally baking the part to level up its structural stats. That is incredible.
It is a powerful technique, but the only engineering catch you have to account for is dimensional shrinkage.
Right, because the polymer chains are relaxing and organizing more densely.
Yes, the part will physically shrink during the baking process, usually anywhere from 0.5% to 2% depending on the material and the infill.
But if you calculate that shrinkage and scale your digital model up slightly before printing, annealing lets you extract the absolute maximum physical potential out of these engineering filaments.
It just proves there's always another layer of optimization to learn.
It makes me think back to that melted PETG dashboard mount sitting in the hot car. It is a frustrating failure in the moment, but it is exactly the kind of failure that forces you to upgrade your skills.
It forces you to modify your hardware and step into the world of industrial materials. The effort is absolutely worth the results.
It is the definitive threshold between a 3D printing hobbyist and a functional fabricator. Well, that wraps up our decision framework for nylon and polycarbonate. For the full numbers, see printera3d.com.